So in chapter 2, we're going to begin to look at measuring location in a distribution. So things like percentile. When you get your standardized test score and they say that you're at the 85th percentile, what is that telling you? And then how is that calculated when you look at everybody that took the test? So the first thing that we're going to talk about is just using those percentiles. We'll look at that today, along with what we call a cumulative relative frequency graph, or an ogive. And then in the next couple of sections or lessons, we're going to look at measuring position using what's called a standard score, or a z-score. So like I said, we're going to start with percentiles. And so a percentile is really looking at the percent that's less than or equal to a certain value. It is important to note here, there has been a change from what your textbook says and what College Board is looking for. It is how I have underlined here, less than or equal to. Your textbook just says less than. It's not strictly less than any longer. It's less than or equal to. So if your SAT score is at the 85th percentile, that means 85% of people scored the same as you or lower than you on the SAT. So here's an example with a small data set. It says Jenny earned a score of 86 on her test. We want to know how she performed relative to the rest of her class. So maybe we look at that 86 and we say, well, that's kind of on the high end, but how high did she perform? What's her percentile? So we can figure out how many students scored less than her. And so her score was greater than or equal to 22 of the 25 observations. So just by counting those up, and then 22 of the 25 is 88%. So she's at the 88th percentile of the class test score distribution. We can also see percentile from what we call a cumulative relative frequency graph, which is also known as an ogive. And here you can see it does look like ogive, but it is pronounced ogive. And so what the ogive does is it gives you cumulative relative frequency for each group or class of a distribution. So think of a frequency distribution like the chart that we made in order to create a histogram. That's what we're doing here, but then instead of just looking at the frequency, we look at the cumulative relative frequency. So here we have age of the first 44 presidents when they were inaugurated. So you've got all of those age classes here jumping by 4-year increments. So 2 presidents were between 40 and 44, 7 between 45 and 49, and so on. So we could use these first 2 columns to make a histogram. We would have 40, 44, 49 on our x-axis, our frequency on y, and then this would give us the height of each of those bars. We could make a relative frequency histogram if we calculated the relative frequency. So 2 out of the 44 presidents, 7 out of the 44 presidents to get those percentages. But what we really are interested in order to make an ogive, is the cumulative relative frequency, or the running total. So cumulative frequency is just that category and then everybody that came before it. So here we're starting with 2. But then this 9 is really the 7 plus the 2 that came before it. So it's everybody that was inaugurated at 49 or younger. The next 22 here is the 13 plus the 7 plus the 2. So really everybody that was inaugurated at 54 or younger. And then we can fill in the rest of the chart that way. So then your cumulative relative frequency is just the cumulative frequency divided by 44. So 2 out of 44, 9 out of 44, and so on. So the very bottom, you should be at 100% because you've got everyone in the group accounted for. So in order to graph, you're going to keep your classes on the x-axis, just like you would if it were a histogram. Your y-axis is your cumulative relative frequency. So it's going to range from 0 to 100%. And then you just put a point at each of those cumulative relative frequencies. So at 44 years of age, we have a point of 4.5%. At 49 years of age, we have a point at 20.5%. And then we continue filling in those values. and then you just connect with a rigid line. So it's not, this one kind of looks like a curve because those boxes are a little bit big, but it's just connect the dots from left to right. So then you can use your ogives to answer some questions. So here, one of them is, was Barack Obama, who was inaugurated at 47, unusually young? Well, 47 is an age, which is on our x-axis. So we're going to locate where that 47 would be. And we can kind of trace up to our graph and then back over to the y-axis to give us an estimate of the percentile. So there's 47. We trace up to the graph and then over to the left. We estimate maybe that's around the 11th percentile. So that's fairly young relative to the other presidents. We can also work in the opposite direction. So here the second question is about the 65th percentile. So 65th percentile is on the y-axis, so we would locate 65 here, trace over to the graph and down to the x-axis to estimate what that age would be. So here, the estimate of age, and that's just going to tell us we think that about 65% of presidents were inaugurated at that age or younger. So we can also calculate what's called a z-score or a standard score. And so what the z-score tells you is exactly how many standard deviations away from the mean a particular observation falls, and then also in what direction. So if you end up with a positive z-score, it's above the mean. A negative z-score, it's below the mean. So here is a formula for you for your z-score, and this is something that you're going to want to memorize because we use it all the time in this course. But you take your particular score minus the mean divided by the standard deviation. Again, like I said, it's a standardized value or a z-score. You also will see this written as z equals mu, which is not mu, x bar. Let me see if I can erase that here. X bar minus mu. Here's my eraser. Okay, so your observation, x or x bar if it's the mean, minus mu for the population mean over sigma, which is the population standard deviation. So those are newer symbols for us. I'm going to put them up here. Mu is the population mean. Sigma is the population standard deviation. Remember from chapter 1, x bar was the sample mean. S sub x is the sample standard deviation. So if the number is describing the entire group, that's the population. If it's describing the subgroup, that's the sample. So we really want to be careful with the way problems are worded and see which numbers we're being given so we can use the appropriate symbol. So here, I'm going to get rid of my notations for sample, mean, and sample standard deviation so that you can read the question. But it does tell us that Jenny earned a score of 86 on her test, which we know from the STEM plot. It gives us the class mean, which is our population mean, and the standard deviation. So we can find her standard score by using our formula. So it's her score of 86 minus the mean of 80 divided by the standard deviation of 6.07. When you do this calculation, just be really careful if you're using your calculator. Make sure you do the subtraction first in your numerator or put parentheses around it. Otherwise, your calculator is just going to do the 80 divided by 6.07. So the order of operations will be incorrect. So that z-score is 0.99, and that tells us how many standard deviations away from the mean she falls and in what direction. So she's 0.99 standard deviations above the mean because it's positive. You can use these scores for comparative purposes. So here we're looking at Jenny still. She took 2 tests. She took a stats test and she took a chemistry test. We want to know on which test did she do better relative to her peers. So it's not which one did she have a higher score, but relative to that class. So we already calculated her z-score for statistics. We did the 86 minus 80 over 6.07. But then for chemistry, it says that there was a mean of 76 and a standard deviation of 4. She scored an 82. So her z-score for chem is going to be 82 minus 76 over 4, or 1.5. In cases like this problem where you're comparing, I would use subscripts like are here. You could even do a Z sub S and a Z sub C just so that you can organize your work a little bit. And even when you're working through the problem, like maybe I might say, I'm going to put boxes around all of the stuff for stats and circles around all the stuff for chem, or just make a little list off to the side with all of my stats stuff, all of my chem stuff. That way I can stay organized. Because if I mix up a mean or if I mix up a standard deviation, then all of a sudden my z-scores aren't going to be what they should be. So that being said, she scored 1.5 standard deviations above the mean here, 0.99 over here. So she did better on the chem test relative to her peers because she was further away from the mean in the positive direction. So your assignment for tonight is page 105, questions 5 to 15, and then tomorrow we will continue with measures of position.